Hello and welcome back to Things Made Simple. If you're new to the channel, we've been working on building an FM synthesizer module based around the YM3812. This is the sound chip that was used in all those classic sound cards of the 80s and 90s, like the Adlib card and the Sound Blaster card. In the last episode, we took MIDI to the next level by adding full 9-voice polyphony, and it turned this breadboard of wires and chips into something that seems like a playable instrument. Well, today we're going to add the ability to choose the way your instrument sounds. But it's also going to require us to take some pretty significant steps back in order to restructure things and make this work. It took me like a month for inspiration to hit, but once it did, the answers were so obvious. I guess that's just the way it goes. But anyway, I have a solution now, and it's not just going to let you choose an instrument to play. It's actually going to turn our instrument into a 16-piece orchestra. And we're going to do this with patches. Patches are just collections of settings that define the sound of the instrument that you want to play. This list here includes all the settings that change the way the YM3812 sounds, and hopefully it should be pretty familiar if you've watched some of the previous videos. One of my ulterior goals for this project is to create a system that doesn't just work with the YM3812, but actually works with other Yamaha FM sound processors as well. And it turns out that by adding just a couple of extra properties, we can come up with a list that does just that. To understand why, let's compare the settings for a handful of different Yamaha FM sound chips. As you can see, many of these are the same, but if you look closely, there's some familial relationships too. All the OPL chips are incremental improvements of each other. The OPL2 added the ability to choose different waveforms, and the OPL3 added even more waveforms, but more importantly, upgraded to 4 operators and the ability to output to 4 separate channels. So you could do stereo left and right, and also rear left and right as well. The YM2151, or the OPM chip, and the YM2612, or the OPN2, took a slightly different path. Both of these chips only support sine waves. However, they use 4 operators to create sounds instead of 2. They also have more complex, low-frequency oscillators that are used to create tremolo and vibrato, and they natively support stereo output and even detuning. The last main difference has to do with the way they define their envelopes. All of the OPL chips support both an ADSR and an ADR envelope. They call the ADR envelopes percussion mode because it doesn't wait for you to release the note in order to trigger the release cycle, so you use these to emulate percussive sounds like a xylophone. The YM2151 and 2612 only support the ADSR mode, but they add a new setting called sustained decay, and that allows you to achieve the same effect and arguably makes the envelope even more versatile. Finally, I just wanted to point out one more thing here, and that is the YM2149, which really isn't an FM chip at all and is sort of archaic next to these other chips, but it did introduce a feature called SSG envelopes. These are basically repeating envelopes that play a sound over and over really fast, and this feature also appears in the YM2612. In terms of the rest of the features, the YM2149 doesn't natively support many of them, but it is possible to emulate things like envelopes and LFOs by manipulating the volume of the channel. So who knows, maybe we can figure that out in a future project. Okay, so now we know what properties each of our chips support. But what about the range of values that are valid for each of those properties? As you can see, the ranges vary widely. In fact, the blue lines are the only ones that are identical. The orange lines indicate the properties that are similar but have different ranges, and then all of the other ones are only supported by one of the 2 chips. But let's take a closer look. Some of these settings aren't really specific to a patch. For example, the global settings affect all of the sounds that the chip produces. And if you tried to play 2 patches that change these settings simultaneously, then they would keep overwriting each other. So we can't really count these inside of a patch. Other settings like frequency and channel are more runtime settings in that they don't really change the nature of the sound. They just affect where the sound's being played or what note you're playing, and so we can kind of eliminate these from the patch as well. That leaves us with this list here. Still, there are a lot of differences, right? Well, if we're going to produce a generic patch, we're going to have to understand why those differences exist. And the answer is bit math, of course. As we talked about in episode 2, the YM chips pack multiple settings together into a single byte. And this means that different settings have different maximum values depending on how many bits get allocated to them. And in fact, the maximum value for every property on all of these chips is going to be these values here on the left. So that means that with a little bit of math, we should be able to translate between them, right? Let's take the attack setting. The YM3812 uses 4 bits to represent this value, while the YM2151 uses 5. So if you wanted to translate this value from a YM2151 patch into a YM3812 patch, then you'd have to right shift this value by 1 bit. Or if you wanted to translate from a YM3812 patch back into a 2151, then you would left shift it by 1 bit. And that kind of works, but as you can see here, you lose fidelity when you go from a lower bit size to a larger one. And then it hit me. Why not just start with the highest possible bit size for every property, and then translate it into whatever any of the chips need? The MIDI standard allows us to send 7-bit numbers without breaking things into multiple bytes, so that seemed like a logical starting point. So let's say we started with a value of 77 out of 127. We could then translate that for the YM2151 by right-shifting it by 2 bits to get to 19 out of 31. Or we could right-shift it by 3 bits to get to 9 out of 15. In both cases, these are proportionally correct for the chip, and as long as we start with that higher value, there's no loss of fidelity. So going back to our list of properties, our patch definition is going to just completely ignore the ranges, and we're going to make everything go from 0 to 127. Our patch also has to deal with the fact that we can have up to 4 different operators, even though the YM3812 only supports 2 operators per channel. Or does it? These are 2 operator algorithms natively supported by the 3812. But along the way, people started to wonder, what if I played 2 different voices at the same time? Wouldn't that be like a 4-operator voice? And, well, I suppose it would be. So I'm going to call these 2x2 operator patches. They use all 4 operator settings, but they're going to be limited to algorithms that sum their output at the end. Of course, the YM2151 that natively supports 4 operators has more algorithms to choose from, but it's worth noting that 3 of these could actually be emulated by the 3812. Okay, back to our patch. For this to work, we're going to have to add a couple of extra things. The processor setting is going to indicate which of the sound chips we want to play the patch on. And the note number is going to be used for percussion instruments, and it indicates which note or frequency to play when we're playing a patch. Lastly, I've included a few options for adding pitch envelopes. This is sort of a stretch goal for me, as they're not natively supported by any of the synth chips, and I'm going to have to emulate these on the fly, but it's easier to add them into the patch standard now than to try to change the patch definition later. So I've plopped them in here, and hopefully at some point we'll get back to these. Speaking of the patch definition, here it is. It's an array of 78 bytes. The first 6 bytes are the patch settings, followed by 4 bytes of channel settings, and then come 17 bytes for each of the different operators. Now that we know what a patch is, let's figure out how to use it. Here are the 9 channels of the YM3812, just waiting to be filled up with instrument patches. Here's an idea. Let's partition the 9 channels up into different groups. Then we can assign a patch to each of the channels in each group. So the first 3 channels might be a piano patch, and then the next 2 might get a trumpet. We could think of each of the groupings as its own sort of instrument. And then when a MIDI signal comes in, depending on the channel, we could choose a channel from the associated grouping to play the note on. This way, it would seem like we have 4 different instruments that we can play. This is actually the first way that I implemented the idea of having simultaneous instruments, and there's some drawbacks and pretty big disadvantages to it. For one, the more instruments we support, the less polyphony you get for each instrument. Also, we can only have up to 9 instruments, and even if we did, they'd all be monophonic. Honestly, this was a terrible idea, so I just completely started over. Okay, let's try this. On the left, we have our MIDI channels, and on the right, we have our 9 channels of the YM3812. What if instead of conceptually assigning patches to the groupings of channels, we assign them to the MIDI channels? Then, when a MIDI note comes in, we can choose a channel using our polyphonic algorithm that we talked about in the last video to select the right channel, and then upload the patch information, and then play the note. Or maybe you play a chord on an organ and it takes 4 notes. Or maybe you strum a chord on a guitar and it takes another 3. Then the brass section comes in and overwrites the patch information for the first 4 channels to play 4 more notes. In this way, the only constraint is that you can only play 9 voices simultaneously. But those 9 voices could come from any instrument. To distill our algorithm down, a MIDI note comes in, we pick the channel on the YM3812, we upload the patch, and then we play the note. And we do that every single time we play a note. But wait, doesn't uploading patch information take a long time? Let's find out. I have my oscilloscope connected to the LED that indicates when data is getting sent to the YM3812. Right now it's in single event mode, so we should get a clear reading of how long this takes. Okay, let me press a few notes all at the same time and see what happens. Each division here is 1 millisecond, and I played 5 notes. So you can kind of see how long each of the notes takes, and it looks like they take about 1 millisecond. Actually, this gap here comes from the fact that I couldn't press all of the notes at the same time. So if you play all 9 notes, we're looking at about 9 milliseconds. Now, is that a long time? Well, in computer time, totally. But in human time, well, let's put this in perspective. Let's say that you played a song at 120 beats per minute. That means that each beat lasts 500 milliseconds. A beat is a quarter note, which equals 2 eighth notes or 4 16th notes, and that means that a 16th note lasts 125 milliseconds. We'll use this bar here to represent 125 milliseconds. This is 9 milliseconds. And honestly, I can't hear it, nor can I even play the notes fast enough to fully overlap them. So I think we're going to be okay. There is one more advantage of continuously reassigning patches to the YM3812. Because we always start with our generic patch and then scale it for the YM3812, and then overwrite all the settings all at once, we never really need to know what's in the chip. And that means we no longer have to keep track of any register information stored in the chip. We can just overwrite it all the time. And that frees up a good bit of our precious little RAM. Okay, it's time to start thinking about code. But before we get too far into the weeds, let's look at how the YM3812 class is structured and how we need to rethink things. As a quick review on where things stand today, we have some functions that send data to the YM3812, and then a long list of functions that use send data to set specific registers depending on the channel or operator that you want to set. And then come the register functions that control whether a channel is playing and the frequency that it's playing. Then we abstract these register functions further with a play note function that takes a MIDI note and then plays it on a specified channel. The getNext function determines, from a polyphony standpoint, which is the best one to use. And if you put these two functions together, you get our fully abstracted note on and note off functions that will play notes with up to 9 voice polyphony while requiring basically 0 understanding of how the YM3812 works. You just pass it a MIDI note number and it plays the note. I like to think of these as generic functions because they work the same whether you're playing on a YM3812 or a YM2151. Everything below the line is YM3812 specific and requires a detailed knowledge of how to use that chip effectively. But if you want to lay a foundation for a library that's going to work across different types of Yamaha sound processors, we need to find a way to take these patch functions and then move them up over the generic line. Let's take a quick look at why we can't do this with the functions that we have today. Say we use one of our functions to set the attack value of operator 1 to the value 12. Well, no problem. That's totally within the range of 0 to 15. But if we set it to 22, which is actually within the range of a YM2151, well, it wouldn't crash, but it would chop the top bit and effectively set the attack value to 6 out of 15. Now what if you set the attack value of operator 22 to the value 12? Well, for the YM2151, again, no problem because there are 32 operators. But the YM3812 only has 18. And since we don't do any error checking in our function, this could have some undesirable results. Now let's set that sustained decay value. Again, no problem on the YM2151 because that property exists, and we would have to write a function for it. But on the YM3812, we don't have that property, nor do we have a function, and it's just not even going to compile. Now, we're going to need a way to handle all of these patch-specific properties more generically. And it turns out we can totally do that, and the way we're going to do it is by taking advantage of this generic patch data structure that we've created. We're going to replace all of these functions with a single send patch function. That function is going to take a reference to one of our generic patches as an input, and then it's going to update the properties of the channel that you specify with whatever settings are compatible for that sound chip. Then up above, we can take our note on and note off functions and replace them with patch note on and patch note off. They're going to operate just like before, except that now you can specify a patch to play every time you play a note. There are a couple of other functions we can add that won't come in handy today, but definitely will later. One that turns off any channel associated with a patch, and another that re-uploads the patch information for any channel that's playing. This will allow us to do things like modify a generic patch property, and then have those updates propagate into the sound chip so we can hear them instantly. Okay, we've made a whole bunch of changes here. Let's clean everything up a little bit. And now let's redraw our generic versus YM3812 specific line. And as you can see, we have the ability now to play a note, but also alter the sound properties in a way that doesn't really require knowledge of the YM3812's operation. You just need to understand how that generic patch structure works. In fact, we could use the same patch structure and rework the entire library pretty easily for a YM2151 that's being used in the Commander X16 platform, or a YM2612 that was used in the Sega Genesis, or even the venerable YMF262, which was used in the OPL3 generation of Sound Blaster cards. And if we want to take this idea even further, we could create a single module that has multiple sound chips and control them all using these generic sound patches. But I'm getting ahead of myself. Let's see how the code functions first for the YM3812. Now, I'm not going to code this thing live because there's just too many changes that we need to make, and I'm worried that it's going to get kind of boring. So, like always, everything's going to be available on my GitHub to study in detail, and today I'm just going to walk through the major changes that I've made. Beginning with a new file called ymdefs.h. This file is going to hold all of the generic definitions that are not really specific to the YM3812. Things like the YM channel data structure that holds the information about what is being played on each of the sound channels. If you recall from the last video, we created an array of these structures in the YM3812 class with a separate instance for each of the 9 channels. And this allowed us to do cool polyphonic stuff. And if you haven't seen that video, I'll leave a reference to it. You should go check it out. We do need to make one tweak to this data structure though. We need to add a pointer to the patch that's been assigned to the channel. Because later when we want to tweak a sound patch, we're going to need to know which channels are playing what patch. Other things I've moved over into this new file include the setBits and getBits macro because they get used by everything. And then also I've added some new global settings that start to define the structure of the patch. Patch gen settings indicates the number of bytes at the start of the patch array that are non-operator specific, so basically the first 10 bytes. And then patch op settings indicates the number of bytes in the array associated with a single operator. The total patch size ends up being the number of general settings plus the number of operator settings times 4, because there's 4 operators. And then we use patch size to define our patch array data structure. This is going to be the data structure that holds all of the settings for a single patch. And a little further down, I've defined names for each index of the patch, and also embedded a table that shows which sound chips support each of the settings either natively or, if there's an asterisk, virtually. Now, if you want to edit a setting in the patch array, you can do so using one of these names. But if you want to modify an operator level setting like attack, well, there are multiple instances of that setting. So to get the right patch index, you start with a name and then add on the total number of settings per operator times the operator that you want to edit. So to change the first operator, operator 0, you could just use patch attack, because you're basically adding 0 times patch op settings. But to change the second operator, you'd have to add on patch op settings. And then to modify the third operator, you'd have to add on patch op settings times 2, and so on. And that should allow you to decide which operator you want to modify inside of the patch. Groovy. Let's move on to the YM3812.cpp file and see if we can implement some of this patch functionality. Most of the magic happens in this new send patch function. This is the thing that compiles all the right settings together for the YM3812 and then sends the data to the chip. And we do that by taking each 7-bit setting in the patch and right-shifting it so it's the right number of bits for the YM3812. And then we left-shift the number so that it occupies the correct bits of the register byte. And then we do that for each of the settings that go into the same byte, and then we OR them all together. And then once we have that composed byte, then we send it up to the sound chip using our send data function. Now I'll leave it as an exercise for the viewer to compare all the bit math with the register map, but I did want to leave you with one other thing, which is if you rewrite this function for the YM2151, it looks surprisingly similar. Next up, we get to replace our note on and off functions with sort of a equivalent patch note on and patch note off functions. Remember, these are the functions that add polyphony by figuring out what channel to play a note on and then tracking the current state of each of those channels, whether it's on or off or what note it's playing. And we track that state in the channel states array, where each element is a YM channel data structure. And remember that we've now updated that data structure to include a pointer to the patch data that's playing on the channel. So in our new function, all we really need to do is take the patch that gets passed in along with the MIDI note, and then store the pointer to that patch in our channel states array. And in our new note off function, when we're searching for the right channel to turn off, we need to find the channel associated with both the note and the patch. Otherwise, if you played, let's say, a C on a trumpet and then a C on a piano, and then turn off the trumpet, well, the piano would turn off too, and we don't want that to happen. We need to ensure that we're turning off the correct instrument as well as the correct note. Okay, one last tweak to make in this file. The channel play note function is the one that handles the intricacies of playing a note. Things like turning a channel off, setting it to the correct frequency, and then turning it back on. And in the middle of that process, when the channel's turned off, is the perfect time to upload the patch information. So in our new function, we call send patch and pass the channel that we're updating as well as the patch that we want to use. Just as a side note, that send patch function expects you to pass the patch itself, not a pointer to the patch, so we do have to dereference that pointer using an asterisk. Okay, we've talked a lot about how to use patches. Now we get to explore how to program them in. This looks kind of complicated, right? Well, it's not so bad. We just have to put all the settings in for all the patches, collect those into an array called patches, and then we do the same thing for patch names and collect them into an array called patch names. And down at the bottom, we can indicate the total number of melodic instrument patches and the total number of drum patches. But before we painstakingly write out all of this code, let's take a quick step back in time to the early 90s. MIDI communication is beginning to take hold, but there just isn't much standardization in place. So the American MIDI Manufacturers Association got together with the Japan MIDI Standards Committee and published the General MIDI specification. Among other things, the specification standardized the sound patches that would be used by compatible instruments. But they didn't standardize the sounds. No, they standardized the names of the patches and left the expression of those sounds up to the manufacturer. 128 names to be exact, and they broke them up into groups of 8, things like pianos or guitars or brass. They also added a named set of drums, which we're going to talk about in a future video. Anyway, the beauty of this is that you can search the internet and find all kinds of patch libraries out there that conform to the General MIDI standard. Now, if you want to create your own patches or convert a patch library that you find on the internet, I highly recommend this OPL3 Bank Editor. It's an open source project, and I will leave a link to it in the description. This will allow you to configure all the sound settings for your chip, preview them, and save them as separate patches. You can even create patches with 4 operators or use those dual 2-operator patches as well. Best of all, you can export all of this information into a standardized DMX OP2 file. And from there, you can use this Node.js program that I created to convert it into the instruments.h file that we were looking at before. Okay, so we've updated our YM3812 library and filled up our patches array with an orchestra full of patches. Now we need to update our main program file and put it all to good use. We'll start by defining the total number of MIDI instruments that we can support, which is 16, one for every MIDI channel. Then for each of our 16 MIDI instruments, we need to keep track of the patch from that giant patches array that's associated with it. We'll do that by storing the index of the patch in this inst_patch_index array. We also need to keep a copy of the patch data that we're actively using for each of these instruments in RAM. And we'll store that in this inst_patch_data array. Note that the type of this array is the patch array that we defined earlier. But wait, aren't we already storing all those patches in RAM? I mean, we created that giant array in the instruments.h file, right? Well, not exactly. Let's take a closer look. Here's an excerpt from that file. Notice this progmem keyword. The AVR microcontroller, and honestly most microcontrollers, follow a Harvard architecture that splits instruction memory from data memory. The instruction memory is where your program code sits, and there's lots of it, 128 kilobytes in this case. And the data memory is what we would typically think of as RAM, and that's where your variables go. You know, things that you need to read and write to. This data memory is a lot faster, but there's way less of it. We've got 13.5K locked up in our patches array, and about another 2K in our patch names array. So it felt like a pretty good idea to just put all the patch information into instruction memory, or progmem as it's called here. But to use that patch information, we need to copy it out of progmem and into RAM. And that leads us to this load patch from progmem function. It takes an index into the inst_patch_data array, and then a patch index that points to a patch in our patches array, and copies the information from progmem into RAM. This way, we only use about 1,200 bytes of RAM instead of, like 15K, and everyone is much happier. Okay, let's move on to the setup function. The first few lines of our original setup function reset the chip and then set up the handlers for the MIDI messages that come in. Then after that, we explicitly define our sound patch one setting at a time and put it in every channel of the YM3812. Well, in our new model, the sound information will be uploaded every single time we play a note, so we really don't have to do that here. In fact, let's just get rid of all this stuff. Now in our new setup function, we're still going to have to reset the chip and set up the note handler functions, but we also need to load patches from progmem into RAM. And so that's what this loop does here. Also, to create some variety, I'm assigning different patches to each instrument incrementally. So MIDI channel 1 is going to play patch 0, MIDI channel 2 is going to play patch 1, and so on. We're also going to have to add another MIDI handler function. This one is going to respond to the program change events. These are kind of standard events that assign a patch index to a MIDI channel. It's a pretty straightforward function. We just take the MIDI channel, which is 1 indexed, and we subtract 1 to make it 0 indexed. And then we take the patch index that was requested and track it in our inst_patch index array. And then finally, we call that function that loads patch information from progmem into RAM. Okay, final change. We have to tweak our note on and off handler functions. Because we replaced the note on and off functions in the YM3812 library with that patch note on and patch note off, so now we have to pass a patch along with the MIDI note whenever we play a note. It's no big deal because we have all the patch information stored in our inst_patch_data array. So we just pass the entry associated with the channel, and we're good to go. Now I know that I've walked through these changes pretty quickly in sort of a piecemeal form, but if you're interested, I highly recommend checking out all the code on GitHub. I've added copious amounts of comments, and I really hope it will be helpful and clarify things for you. But for now, I'm going to compile this, and we're going to give it a whirl. It's demo time.
So the first thing we're going to do is we're going to test out the program change event. That's the MIDI event that you can use to select different patch numbers. And the way the keyboard works that I have, it actually has a set of buttons that are assigned to different patch numbers. And when you press it, it just sends whatever that number is that's associated with it. So I'm going to just flip through some buttons, and that's going to flip through some patches, and just get ready to experience some nostalgia, because these sounds totally bring back memories, at least for me. All right, let's do it. Okay, now I want to test out having multiple instruments playing at the exact same time. But I can't do that with my keyboard, because I can really only just play one patch at a time on that. There might be a way to split the keyboard, but whatever. I'm going to use Ableton, and I'm going to dial in a melody that's going to go across multiple different MIDI channels, and each MIDI channel will be assigned to a different patch. That way we'll get different sounds. So let's give it a go. Well, I hope you've enjoyed going on this journey into the world of patches with me. This was a pretty big shift in my thinking. I'm sure it's probably super obvious, and it's certainly obvious in retrospect, but this was a pretty big shift in my thinking as I was building out this module. And it opened up a world of different kinds of opportunities in terms of making drum sounds and making these 2x2 operators that we're going to get to in the next video. It also drastically simplified the code, and it gives us the ability to create these multi-chip modules as well, which eventually we're going to explore, I think, in another video after I get through this module. But it does work. I've tried it. It's pretty cool, actually. Anyway, I just wanted to say thank you for watching, and if you like this video, hit like, hit subscribe, and we'll just see you next time on Things Made Simple.